Hello everyone and welcome to the 29th lecture of the course Advanced Structural Analysis. We have briefly seen the approach of implementation of the stiffness method, which is good enough to be implemented in the computer systems. Now, the similar method we will try to apply to some of the problems, and to start with we will take a continuous beam system. We will apply the first numerical case in which we consider the problem from the respective parameters, which will also be important for us to implement the similar idea in a computing environment, and then we will also try to see in the subsequent sessions the similar discussions using a standard MATLAB code. Now, you can also refer the course page where already the MATLAB related instructions have been provided. There are some of the basic information related to working of the software program is included, and you all have been also been provided with the free access to the MATLAB environment. So, you can do some sufficient practice on the basic module, so that the given concept which we will discuss in the subsequent sessions will be clear to you. So, as we have seen the computer oriented stiffness approach, we have discussed the overall content of it. We understand that the steps of the given problem are: we initially identify all the input parameters, because now we are also thinking it not from the perspective of a user which is doing it manually, but we are trying to put all these parameters into a computer program which will try to run it. So, as a user visualizes a problem, in the similar manner we need to put all the input parameters for the computers also to understand, and for that aspect we define very clearly what are the input parameters required for the problem at the beginning, and we provide all that information to the given program so that it can run the analysis for the requisite cases. Now, when it comes to the input parameters, we can understand that what initially is required to be known is the member data. One must know that how many number of members are there, corresponding to each of the members, what are their lengths, what are their elastic properties of the given system. So, the cross section of the given members, the second moment of area or any other values associated with the members should be provided as an input parameter to the given system. At the same condition, one must also provide the nodes and the node connectivity to the given system, which means that in a given system I must provide the inclusion of the given system with respect to that how many number of nodes it is going to have, and then for each of the member what are the node connectivities which are considered, which means that if I provide the data for this given beam member, I have to say that this is the joint 1, this is the joint 2, this is the joint 3, and this is the joint 4. So, there are 4 number of nodes which need to be told to the program. At the same time, when I go with the member contributions, I must also tell that for member 1, the node 1 and node 2 are the connecting nodes of the given problem. Similarly, when I go to the member 2, I must also identify that node or member 2 is having the node 2 and 3 as the connecting nodes of the given system. As we go to the trusses, the similar idea also need to be reflected. We define it as the respective joints on the given problem, and corresponding to it, now I need to define for each of the members. So, if I say that this is say some member number I have to say that corresponding to the member I, the connecting nodes of the given problem are 2 and 6 for the given case. So, this is one information which one need to provide. Similarly, I also need to provide the degrees of freedom in the given problem. Now, one can correlate this idea also with the support conditions which we typically identify. All the degrees of freedom which are supported will be restrained. So, those will be the degrees of freedom which we need to specify that at these positions the degrees of freedom are restrained, and then at the same time we need to include from that the idea of the overall degrees of freedom which are free or which are allowed to deform in the given system. And at the end we need to define the loading condition of the given problem, which includes that any kind of a loads which are active at the respective joints directly, any kind of a loads which are active at the spans of the given members, and corresponding to these informations the system should be able to understand, or the code should be able to understand the contributions of the individual loading vectors of the given system. Now, before moving into the further discussion and the problem statement, now we also try to make this point very clear that for general structural analysis we use multiple software tools. All these software tools typically work on a standard CAD modules in which we define the geometrical aspects of the given system, we provide the input data of the members. Eventually, whatever we are doing in these software tools is the identification of these input parameters of the given system. So, if in a software tool I am able to draw a truss like this, then the software module is able to understand that yes, there are different members which are labeled like this, and for each of the member the software is also able to understand that what are the connecting nodes of the given problem. In the similar manner, when the user is able to select a given material case and specify it to the given member, the software is also able to understand that what is the member data in terms of its material properties or its geometrical properties of the given system. In the similar manner, once we use any kind of a support condition which are provided in the given software module, the system is also able to now understand what are the degrees of freedom which are free and the degrees of freedom which are restrained due to the support conditions of the given problem. So, the algorithm which we typically try to discuss is the generalization of any of the software module which we utilize for our general structural analysis. As a next step, we identify the overall member stiffnesses and the global stiffness of the given system. These member stiffnesses which we are defining are all in the respective global coordinates of the given system. At the same time, we also identify the load contributions of individual members and we assemble that to get the overall load vector of the given system. Finally, based upon the available free and the restrained degrees of freedom of the given system, we rearrange the matrix of the given stiffness matrix and the load vector, and then we try to evaluate the solutions of the given system. Once the basic solution is known or calculated, we move to the post computation for the given system. So, these are the basic steps which we will try to look, and now we will move ahead with one simplified problem which we have identified over here. So, this is a beam which is subjected to some kind of a load. We have also highlighted a different color on the given system which identifies that the span of the given beam is also provided with a different flexural rigidity of the given system for the span B to D, whereas span A to B is having a flexural rigidity of the value E I for the given system. At the same time, the respective other input parameters of the given system are shown. Now, how do we input or how do we provide these input parameters to the given system that we can identify? We first provide one input data sheet which is for the members. We say that let we have all the members and their data in the given system. We have the member 1 which is AB, member 2 which is BC, and member 3 which is CD in the given problem. So, these are the 3 members associated with the given problem which we have identified in the given system. Now, for each of the member we define what are the lengths which are L, L and 2L on the given system. One can also go with the coordinates of the given system and they will automatically calculate the length of the given system. The second case, we define the EI values which are also provided as an input case for the given system. And then we also define that for any given member what are the 2 of the joints, the end joints of the given problem. Now, for doing it beforehand, I have to label the given members. I have to say that this is the joint 1, this is the joint 2, this is the joint 3 and this is the joint 4 of the given problem. And as per the labeling of the system, this is member 1, this is member 2 and this is member 3. So, for member 1 I have a joints J and K which are 1 and 2. For member 2 I have joints J and K which are 2 and 3, and for joint member 3 I have a joints 3 and 4 which are reflected by the idea of J and K in the given system. I also realize that for any of the joint J there are 2 degrees of freedom which are associated, which are 2J minus 1 and 2J. Similarly, for the joint K there are 2 degrees of freedom which are associated with it, and those are 2K minus 1 and 2K in the given system. Similarly, now I move ahead with the idea of the support conditions and the identification of the condition whether it is a restraint or not. So, with this point we identify that how many node numbers are defined in the given problem, as we have already located earlier that there are 4 joints in the given problem. So, now for each of the joint we have 2 degrees of freedom identified. One is the degree of freedom as a translation in the vertical direction y, and second the rotation at the given system about the axis z of the given problem. Now, I will identify at each of the point what is the state of these 2 degrees of freedom in the given system. That means, at node 1 whether the degrees of freedom in the direction y and theta are restrained or not. If we provide that yes they are restrained, we give the number 1, and if we say that these are not restrained, we give the number 0 for the given system. Now, this is a very standard way of providing the argument to the computer system. Even if we are doing the problem manually, we can consider it by giving these similar numbers. Later on we can reflect this idea on a generalized code as well. So, similarly, we have defined for the joint 2, 3 and 4 also the conditions of the restraint in the given problem. We realize that joint 1 which is fully restrained, so both the numbers are 1, joint 2 which is fully free, so both the numbers are 0, joint 3 which is free to rotate, so the theta contribution is allowed, whereas joint 4 which is again fixed has been fully restrained with the given system. Now, this is as per the order of the degrees of freedom as well which we have defined in the given problem. Now, once we identify these contributions, we now move to the second step which is identification of the member stiffness, and these member stiffnesses are also defined in the global coordinates. Now, most importantly, if we look at the given system, these are the global degrees of freedom of the given system, but at the same time if I bring out any of the member out of here, I realize that the individual member degrees of freedom are also in the same direction, which means that for continuous beams or simple 1D elements like beam members, the coordinates which are identified for the local member parts are in the same direction as the global coordinates of the given system. And this is why the identification of the stiffness matrix for the member stiffness is easier, as we do not need to do any transformation in the given system. So, I utilize the stiffness matrix for the member 1, member 2 and member 3 based upon the initially given formula. One can again refer the first lecture of the 6th week, where we have discussed the details of the different stiffness contributions of the given system, and based upon the simple idea of the beam, we have now identified these stiffness contributions for member 1, 2 and 3 in the given problem. What we will also do at the same point, we realize that each individual member is catering to the specific nodes of the given problem. So, we will also locate these individual stiffness contribution with respect to the global degrees of freedom which they are going to contribute to, which means that when I look at the member 1, I realize that member 2 is connected to the two of the joints which are joint 1 and 2 of the given problem, and if it is joint 1 and 2, it is going to include the contribution to the degrees of freedom which are 1, 2, 3 and 4 in the given system. So, I will now say the SM1 which has been identified is going to go to the overall stiffness matrix or the global stiffness matrix in the position of the rows and columns 1, 2, 3, 4 and 1, 2, 3, 4. Similarly, I move to the member 2 and I realize that for the member 2, the respective ends of the given system or the joints of the given problem are defined as 2 and 3. So, corresponding to the joint 2 and 3, I define the respective degrees of freedom, and these degrees of freedom are now labeled as 3, 4, 5 and 6 in the given system. So, now I will say that the contribution of the member stiffness 2, which is again in the global directions, is going to be added to the respective degrees of freedom 3, 4, 5 and 6 in the given system. So, it will be added to the position of 3, 4, 5, 6 rows and columns in the global stiffness of the given system. Similarly, now we can easily draw for the member 3 also. Member 3, we understand that it is connected to two of the nodes which are the nodes 3 and 4 of the given system, and the degrees of freedom which it will entertain, those are the degrees of freedom 5, 6, 7 and 8 in the given problem, and accordingly I will just label the numbering of the given system that the degrees of freedom should be assigned to this given problem or this given member as 5, 6, 7, 8, 5, 6, 7, 8 of the given system. So, knowing these values, now I can easily place the stiffness contribution of the member 1. So, I can bring this stiffness contribution which is identified over here and place it directly in the position of row number 1, 2, 3 and 4 and column number 1, 2, 3, 4 in the global system. Similarly, I can bring the contribution of the member 2 and I realize that it is corresponding to the rows in column 3, 4, 5, 6. So, I will bring the contribution of the member 2 and say that in the position of row number 3, 4, 5, 6 and column number 3, 4, 5, 6, this contribution will be added. Similarly, I will bring the member number 3 and its stiffness contribution. I will see it is in the direction of 5, 6, 7, 8 degrees of freedom. So, I will come to the row number 5, 6, column number 5, 6, 7, 8 and the row number 5, 6, 7, 8 and I will add the contribution in that position of the given system. We have already said that wherever there is a overlap which is appearing, we will simply add the contributions of the previously existing system and on top of it the new contribution has been added. So, for member 1 we added the contribution, for member 2 also we added the contribution, and finally, for member 3 also we added the contribution. Once we are done with all these contributions added in the given system, we can describe that this is how the overall stiffness matrix will appear for the given problem. The standard idea of the stiffness matrix which has been defined for the given system. So, I can just now generalize the given problem that this is the stiffness matrix which has been identified with respect to all the degrees of freedom 1 to 8 in the given problem, and it has been created or assembled by taking the contributions of the stiffness for the member 1, stiffness for the member 2 and stiffness for the member 3 in the global coordinates. Now, the next task which we identify is the identification of the similar stiffness matrix in a regular process, because right now we had 3 number of members, it was much more easier for me to do it manually. But in case if we have a larger number of systems, how do we manually do it, or how do we do it in an automated manner? So, we say that for a global system, if we have n number of joints, the overall size of the stiffness matrix which we are trying to assemble will be 2n cross 2n. The number of members which are there in the system, I can say that those are m. So, I will run a loop which will go for each of the member from member 1 to m in the given system, and then corresponding to any of the member, we realize that if I am talking about the member I in the given problem, it has two of the joints which are located as joint j and k in the given problem. So, I will bring the numbers j and k for the given system, because as I know that corresponding to the ith member I am talking about. So, I will also know that it has two of the joints which are joint j and k of the given problem. So, I will now say that this is going to contribute to the 4 degrees of freedom, which are 2 of j minus 1, 2 of j, 2 of k minus 1 and 2 of k in the given system. So, I can arrange all these 4 degrees of freedom of the given system and say them that these are the 4 values assigned to the given member I in the given problem. And now, I will say that in the global stiffness matrix at the position of these 4 degrees of freedom, which are d1, d2, d3 and d4, I will just be placing the stiffness contribution of the member I. So, stiffness contribution for the member I, which happens to be a 4 cross 4 stiffness, will be placed in the position of the d of I comma d of I. If you can just now see this particular statement, one can understand that this is the contribution which is added with respect to the rows d1, d2, d3 and d4 and columns d1, d2, d3 and d4. At the same time, while doing this step, I should not forget that any of the contribution which is already existing in the global stiffness matrix should also remain there. So, that means that if you will simply add the contribution, you will replace it, probably the previously existing value will be superimposed and will be nullified from the given system. As we do not want to do it, we will also add that previously existing value, let that be there, and at the same time add the contribution of the member I in the given case. So, for these cases, what we typically do, we initially generalize, we will show it in the code as well, that we initially say that the standard size of the S of g, which is 2n cross 2n, is populated with all the values being 0, and now we will keep on adding the contribution of each member contribution in the given system. So, this is a standard way by which we can generate the overall global assembly of the stiffness matrix. Now, in the same manner, I can go with the assembly of the load vector as well. We have already shown this example earlier. We have said that now, if we in the given problem we want to highlight, we have considered that this is member 1, this is member 2 and this is member 3. Corresponding to each of the members, we have identified that they are subjected to some end forces which are located on the given system. At the same time, there are some joint forces also which are active. So, if you remember the numbering of the joints, we have defined that this is the joint 1 to 4 which are defined in the given problem. So, one can easily first break down that the joint forces can be located in the given problem, and the joint forces corresponding to these 8 degrees of freedom can be located as 1, 2, 3, 4, 5, 6, 7 and 8. So, I will go with the joint 1. The 2 degrees of freedom, they are not having any of the joint load directly active here. So, the values are 0. We must recall that A of j refers to the loads which are directly active at the joints of the given problem. So, they are not the part of the member load, but they are the directly active joint loads in the given problem. Similarly, the joint 3 and 4 the contribution of the degrees of freedom 3 and 4, which is corresponding to the joint 2. So, I see here that there is a load which is downward, so minus p, and in the direction of the 4 we have a moment which is p of L in the given problem. Then I move to the joint 3, corresponding to which we have 2 degrees of freedom 5 and 6, and there is no force on that. So, there is 0 contribution for this given system. And finally, we move to the joint 4, there also we have no contribution of the load. So, corresponding to it 2 degrees of freedom 7 and 8, and they will also be 0. So, with this idea in mind, we have identified that what is the A of j in the given system. The next part which we need to do is the contribution of the equivalent joint loads in the given problem. And to define the equivalent joint loads, we say that we first define the equivalent member reactions in the given system, the fixed ended reaction of each of the members, and then we replace them or place them in the appropriate positions in the global assembly. Now, for the member 1, we calculate the member force which is applied, the member load of the amount p, the overall length of the system is L. So, we have calculated the reactions P L by 2, P by 2 and P L upon 8 as the moment in the given system. One can easily describe now the A of M1 with respect to the fixed ended reaction can be defined. If I will locate these values, it will come out as P by 2 in the direction of degree of freedom 1. In the direction of degree of freedom 2, it is the moment which is P L upon 8. In the direction of degree of freedom 3, it is again P by 2, and in the direction of degree of freedom 4, it is minus of P L upon 8. So, these are the degrees of freedom direction 1, 2, 3, 4 in the local coordinates of the given system or in the local system or the member. but at the same time when we locate it with respect to the generalized coordinates of the global system, we realize that member 1 is going to contribute with respect to the joint 1 and 2, and they have their own degrees of freedom which are 1, 2, 3 and 4, which are also in the similar order. Similarly, I go to the member 2. I define that corresponding to the member 2, the fixed ended forces can be described. This is again P, the second one which is PL upon 4, third one which is P, and the fourth one which is minus of PL upon 4 in the given system. But at the same time, what I also realize, now member 2 is going to contribute to the joint 2 and joint 3 of the given system. Joint 2 is having the degrees of freedom 3 and 4, whereas joint 3 is having the degrees of freedom 5 and 6 in the given system. So, I will say that the member force 2 is going to contribute to the degrees of freedom 3, 4, 5 and 6 in the given problem. Finally, we move to the member force 3 as well, and we describe the contributions for the given system. We write the values again. This is 1 which is P, PL upon 3, the third one which is P, and the final which is minus of PL upon 3 in the given problem, and we locate that this is corresponding to the member 3 which is having the joint 3 and 4. So, it will be associated with the degrees of freedom 5, 6, 7 and 8 in the given problem. So, knowing these values, now I can easily assemble the overall E of E, which is the equivalent joint load vector of the given system. I can bring the idea that, so we can just see it that these are the values which we have just identified for overall system. The value corresponding to the member force 1, member force 2, member force 3, these are all the values which have been evaluated with respect to the fixed ended part. That means, they are the part of the reactions in the given system. As a next step, to identify the given system, I go back to the calculation of the equivalent joint load from here. I say that the member 1 is contributing to the degrees of freedom 1, 2, 3, 4. So, I will bring these components in the direction of member 1, and I say that this is P by 2, this is PL upon 8, this is P by 2, and this is minus PL upon 8 in the given problem. At the same time, I realize that these are the fixed ended forces, which means that these are the reactions of the system. So, when I convert it into the equivalent joint load, I should just reverse the direction of these forces. So, that is why I just add the minus sign with that, and that is where it brings out the value of minus P by 2, minus PL upon 8, minus P by 2 and PL upon 8 in the given system. Then I go to the contribution of the member 2. I realize member 2 is contributing to the degrees of freedom 3, 4, 5 and 6 in the given problem. So, with this idea in mind, I add the values on the existing values which are already there in the direction of degree of freedom 3. As I do it with the negative sign, so minus P, minus of PL upon 4, and then corresponding to 5 minus of P, and then corresponding to 6 PL upon 4 in the given system. Similarly, finally, I move to the AM3, which is going to give me the corresponding contributions for the degrees of freedom 5, 6, 7 and 8 in the given problem. And if I just add that again with the negative sign, I get it as minus P minus PL upon 3 minus of P and PL upon 3 in the given system. So, with this idea in mind, now we realize that we have calculated the assembly of the equivalent joint load also. A of j was already known to us. So, we will just add on top of it this contribution which we have included, and finally, we will get the overall resultant load vector which we need to assign for the given system. So, this is the overall resultant load vector which we require, having a size of 8 cross 1 in the given system. We have also assigned the 8 cross 8 stiffness matrix of the given system, and this way we have now the overall contributions of the stiffness as well as the joint load vector available to us. With this point, now we can move ahead with the contribution of the individual cases with respect to the free and the restrained degrees of freedom, and that brings us to say that in the original problem, as the degrees of freedom which have been identified, they are all the global or the standard order of the degrees of freedom as we have identified. Now, out of that we need to identify the degrees of freedom which are free and restrained in the given system. So, if I now look at the given system, I say that the degrees of freedom which are free in the given problem, they happens to be the degree of freedom corresponding to 3, 4, then at the position of the given support here we have degree of freedom 6 which is free. Then corresponding to the degrees of freedom which are restrained in the given system, we realize that at the joint 1 both the degrees of freedom are restrained, at the joint 2 both are free, so they are not included, at the joint 3 degree of freedom 5 is restrained, and at the joint 4 degrees of freedom 7 and 8 both are restrained in the given problem. So, now I need to rearrange the given matrix so that I can arrange it in the order of the standard solution method which we typically require for the given case, and that is what we will start to look in the next session. So, we have briefly implemented the computer based stiffness approach for the continuous beam systems. We have identified the global joint load vector as well as the stiffness matrix of the given system, and with the subsequent session we will now look at the approach of identifying the contributions with respect to the individual free and the restrained degrees of freedom of the given system. With this we stop over here. Thank you everyone.